In this lecture we are going to learn about what we call the second order linear differential equation. So let's do a second order linear differential equation. So what's the second order linear differential equation? A differential equation of the form ax y double prime plus bx y prime plus cx y equal to fx is in the second order linear, is in second order. Order means the highest derivative. You can see the highest derivative is 2. So it's in second order linear non-homogeneous form. Okay. It's in the form of second order linear non-homogeneous. Second order linear non-homogeneous. So all these terms are important. Second order means degree 2. Linear means all the coefficients functions are functions of independent variable only, and there are no other products of y. And non-homogeneous because there's a fx term which may not be equal to 0. Okay, so ax, ex and cx are functions of the independent variable, in this case x. Okay, good. So now what we can do, if we have an equation like that, we can divide by x. We can divide by the coefficient of the largest term, or largest derivative term. We can divide by that, and once we divide by that, we can write this form in a different form. So we can say dividing by x, we can write this differential equation in this form: y double prime plus px y prime plus qx y equals to fx, like that. We can write it in this form. So where px equals to bx over ax, and qx equal to cx over ax, and small fx equal to fx over ax. And then what's going to happen if fx equal to 0? This differential equation become a homogeneous equation. So if the fx equal to 0, then we have y double prime plus px y prime plus qx y equals 0. We have the homogeneous equation. So this is homogeneous. So that is the goal of the goal of this one is to how to solve this. So we're going to focus on this differential equation. So the goal is to solve this. So we can talk about several different techniques, not in this lecture, but later. But we're going to talk about the basics here. So this is the focus. Okay, y double prime plus px y prime plus qx y equals 0. So we already know some examples. So let's look at like 2 examples that we know already. So we know that, so the examples, we know that y double prime plus k squared y equals 0. So we talk about these 4 formulas. We all know the solution of this one, because you can see we can write this one as y double prime equal minus k squared y. So this is the simple harmonic motion. So the solutions we have y1, that's one solution, which is cosine k x, if you consider x as the independent variable, and we have y2, which is sine kx. So we know 2 solutions. So that's a second order linear differential equation. And also we know another one, so that's 1. We also know this one, y double prime minus k squared y equals 0, because this you can write as y double prime equal k squared y. So this has actually 4 type of solutions. So what are the solutions for this? So the solutions of this one is, so you can say y1 equal e to the kx, and then e to the negative kx, e to the negative kx, and we'll call y2 e to the negative kx. And also we know that we can write the solution using hyperbolic functions, hyperbolic trig. So we can say another solution is y1 equal cos kx, and also this is 3, and then y4 is sine shin, not sine, shin, because it's hyperbolic sine, shin kx. So we have these 4 solutions for that. So there are 4 solutions. Now the next result says that if you combine any 2 solutions, that's still a solution of the original equation. That's quite interesting result. So let's talk about that. It's called the so it's a theorem. It's called the superposition principle. Superposition principle. So what it says that suppose y1 and y2 are 2 solutions of the homogeneous equation of the homogeneous differential equation y double prime plus px y prime plus qx y equals 0. Then yx, which is a constant times y1 plus another constant times y2. y1, y2 are the previous solutions that you know. Then is also a solution. Is also a solution of star for any C1 and C2 which are constants. So this is what we call the superposition principle. So it's a very powerful result, and we're going to use this a lot throughout the rest of the course. So what it says that if you know 2 solutions, if you consider, this is what we normally call a linear combination. So if you consider any linear combination, this is what we call a linear combination. So if you consider any linear combination, it says that it is also a solution. Any linear combination is also a solution. So let's see how we're gonna prove this one. So this is like interesting result. So we're gonna prove this result. So let's look at the proof. So the proof. So suppose that y1 and y2 are solutions of the second order linear homogeneous differential equation, y double prime plus px y prime plus qx y equals 0. Then what you can do, because we know that these are solutions, that means should satisfy the differential equation. So we can write y1 double prime plus px y prime plus qx y 1 equals 0, because y1 is a solution, so it should satisfy the differential equation. And we can also write y2 double prime plus px y2 prime plus qx y2 equals 0, because y2 is a solution. Now what we can do, we're going to consider the linear combination. So now consider y equal c1 y1 plus c2 y2. So what we're going to do, we're going to define this new function and we're going to plug in that to the differential equation to the left side of the differential equation and see whether we can simplify. Okay. So if this is the case, now what we can do, we're gonna plug in this to a differential equation. That means we need to find the first and second derivative. So let's find the first and second derivative of this one. So the first derivative of this is c1 is a constant y1 prime plus c2 is a constant y2 prime, and the second derivative is c1, which is a constant y1 double prime plus c2 is a constant y2 double prime. Now what we can do, we can substitute. Okay, then by substituting, we have y double prime plus px y prime plus qx y equals, so what we can do, I'm going to substitute now. Y double prime is what? c1 y1 double prime plus c2 y2 double prime, that's y double prime, plus px times y prime is what? c1 y1 prime plus c2 y2 prime. So what I did, I substitute, and then plus qx times y equals to c1 y1 plus c2 y2. What I did, I substitute for the three terms. So you can see that's that term, and this one is that, and then we can substitute for that's the y. So what we can do is we can collect terms. So what I'm going to do, I'm going to collect the y1 terms and y2 terms separately. So let's collect the terms separately. So let's go with the y1 term. So if you go with the y1 terms, so you can see so you're going to get c1 times y1 double prime plus, that's the first y1 term, and then we have this one and we have that one. So let's combine all three, and then we have y2 terms. These are y2 terms, this, that, and so we're going to collect them separately. So let's go with the y1 terms. So we have that, and then we have px, c1 is out, y1 prime plus qx c1 out y1. So that's the y1 term, and then go with the y2 term, which is c2 times y2 double prime plus px y2 prime plus qx y2. But what do you know about those two terms? And we know that since y1 is a solution of the differential equation, this term has to be 0. So this term is simply 0. So this term is simply 0, is equal to 0. The same thing goes with that, because this is a solution of the differential equation. So this is also equal to 0. So those two terms are 0. That means you're going to get 0. So you get 0. So that means yes. So once you plug in, so you get 0. That means it is a solution. Okay, good. So you can see thus yx, which is c1 y1 plus c2 y2, is also a solution for any, that's the important part, for any c1 and c2. So you can see that it doesn't matter what c1 c2 you use, that's still a solution, because those two terms are 0. Since they are 0, it doesn't matter what the c1 c2. Good. So that's like very powerful result. That's what we call the superposition principle. So that means if you know two solutions, you can simply consider any linear combination. That's also going to be a solution. Now what we can do, we can talk about another idea, like how to prove this in a kind of simple way. So that's what we call a L operator method. So let's talk about that. So L operators, L means linear. So linear operator method, L operator method. So we can prove this result in a very easy way using a new method called L operators method. So we can define an operator. Like we already know like two operators. One operator is a differential operator that you learn in Calc 1, and another operator is what we call the integral operator that you learn in Calc 1 and Calc 2. So those are linear operators that you already learn. So operators. So we can see. So we can write this differential equation y double prime plus px y prime plus qx y equals 0 can be written as Ly equals 0, where, so what we can do, we can take the differential part out. So that means where L is simply, we take the operator part. That means C is a y double prime. That means the second derivative. So we can write like this, d squared dx squared, like that. So we can take, that's the operator part. What's going to happen? This operator act on a function, then you get the second derivative. So that's operator. And then plus, what upon the second term? Second term you can write as px d over dx without the y function, plus other one is just qx is an operator, where is an operator. It's an operator. So one example is like this. So let's say d over dx, that's operator. So if this act on x squared plus x cube, what's gonna happen? If this operator act on this, so you're gonna get you can operate on the first one, so you're gonna get 2x, that's the first derivative. Operate on the second one, so 3x squared, that's the second term. So if the operator act on that, so you're gonna get those two functions. So that's what mean by a operator act on a function. The same idea. So we just take the operator part out. And also from linear algebra we talk about what we call linear operators. actually this differential operator is a linear operator, so that makes most of those calculations simple. So both the differential operator and the integral operators are linear operators. So we also see that so L is a linear operator. L is a linear operator. L is a linear operator. L is a linear operator since L is a real linear operator since the first one, you can see if L operate on two functions y1, y2, you can actually write this one as L operate on the first one, L operate on the second one. That's the first condition of a linear operator. The second condition of a linear operator is L. If you have a C constant times a function, what you can do is you can simply pull the constant out. That's the second condition. So what the first condition says, if you have a sum, you can write as a so it's a operate on a sum is sum of operators, and the second one is if you have a constant, you can pull the constant out. So pull the constant out. So that's the second condition. The first condition, if you have a sum, you can write this as two separate. So if operator satisfy these two conditions, we call it as a linear operator. If operator satisfy these two conditions, we call it as a linear operator. So the examples are so we can see two examples. Examples are, the one is the differential operator d over dx, that's one, that's operator, and then you act on a function. So the second one is the integral operator, so you integrate on a function, that's the operator. So we write the operator like that, so we put dot, so that is the function that you can operate on. So this is how we write operator. So we already know two linear operators. One is the differential operator, the other one is integral operator. Now let's see how we can use this idea to prove our result. So let's go back to the proof. So the proof second method. Proof the second method. So what we can do, so we know that so we need to show that y is also a solution, so that's the y. So now what we can do, we can operate on the two functions, but we know that L is a linear operator, and L is the same one, so L is that one we define here. So then what's going to happen, then you consider Ly, which is L. What is y? It is C1 y1 plus C2 y2. This is a linear operator, therefore we can break it into two, so it's L C1 y1 plus C2 y2. No, it's the same thing, so we can break it into two. So once you break this into two, so you can get that plus L C2 y2. Now using the second condition, this is the first condition. Using the second condition, we can pull the C1 out. So if you pull the C1 out, C1 L y1 plus C2 L y2. But we know that L y1 equals 0 because y1 is a solution. So this is 0. And this is also 0. So that means you get C1 times 0 plus C2 times 0, which is 0. So that's how you use the L operators to prove the result. Okay. So here I use the first condition. Here we use the second condition. So we use the two conditions. We use the first condition, that's you can split a sum. That's the first condition. And the second condition says if you have a constant, we can pull it out. So once you do that, then you end up getting this, because we know that L y1 equals 0 because y1 is a solution of the second order linear differential equation, and then L y2 equals 0 because that's also a solution. That means if you combine them, so you get 0 0, so C1 0 plus C2 0, so which is 0. So that's a proof. Okay, so very easy proof, and so you can use these L operators in certain situations to make those very lengthy proofs short. Good. So let's go to the next very important result. So what it says that this is a existence and uniqueness result. We are not going to prove, we just give the result. So this is like another theorem. So it is a existence and uniqueness. This is for second order. So what it says that suppose the p function, q function, and the small f function are continuous. Functions on some interval I containing a is a number containing a, then the equation y double prime plus px y prime plus qxy equal fx has exactly one solution. That's what we call a unique solution. Has exactly one solution. Defined on some interval containing a. Defined on some interval containing a. It may or may not be equal to I. It may be little smaller than I. Satisfying the initial conditions, containing a, satisfying the initial conditions y a equal to some number and y prime a equal to another number. So that's the interval you talk about. So there's an interval, that interval I, that's the original interval I, where those three functions continuous. A is somewhere, and then inside this interval you may find another interval. So it might be equal to I or it might be little smaller than I. So that's the second interval you talk about. So where b0 and b1 are constants. Okay. So for to any constant like that, ya equal b0 and y prime a equal b1, so it says that there is if the three functions px, qx, and fx are continuous, then the theorem says that there is a unique solution to this differential equation. This is this non-homogeneous equation. There's a unique solution to this differential equation. It's kind of interesting. So geometrically, what this means? So it says that we know two things. We know a point, and we also know the slope at that point. So we know those two information. We know the point, and we also know the slope. So we know the point, and we know a slope, which is b1. So if you know a point and a slope like that on an interval containing I, that's I, it says that then you can uniquely solve this differential equation if px, qx, and fx are constant. If p, q, and f continuous are continuous, then there's a unique solution. There's a unique solution. But unfortunately, it doesn't tell you how to do it, but the theorem says that there is unique solution, and that's it. So these kind of problems are what we normally call the Cauchy problems. It's called Cauchy problems. Cauchy problems. You know, point and the slope. It's called Cauchy problems. There are other kind of problems, but this is what we call the Cauchy problem. So and then so according to theorem, so there's a unique solution. So that's the unique solution you're gonna get. So the goal is to find this. That's the goal of this this lecture and the future lectures. How to find this? This can be a little complicated. It's not like easy as first case. So let's have a little note about this. So note: if y1 and y2 are two solutions, if y1 and y2 are two solutions, of the homogeneous equation then we know that, we just learn about this one, then we know that y equal c1 y1 plus c2 y2 is also a solution. So we just learned that. That's the case. If you know two solutions, then any linear combination of that is also a solution. But remember, this is the homogeneous equation. What we talked about just a few minutes ago was the non-homogeneous. So that's the difference. Okay, just compare. This is the homogeneous equation. For the homogeneous, if you know two solutions, then there are infinite many solutions like that for any C1 and C2. But what we just talk about is the non-homogeneous equation. In that case, there's a unique solution. Okay, good. So let's look at a special case. So this is just an example. The equation y double prime plus k squared y equals 0 with y0 equal b naught and y prime 0 equal b1 has the solution yx equal b naught cosine kx plus b1 over k1 b1 over k sine kx. And also the equation y double prime minus k squared y equals 0 with y0 equal b naught and y prime 0 equal b1 has the solution yx equal b naught cos kx plus b1 over k sin kx. So you can see the similarity between the two, the harmonic solution and the hyperbolic solution. So only cos become cos and sine becomes sin. And also how we know that those solutions are unique, and you can see the conditions. What are the conditions that we have? So we can see that in this case px, which is equal to 0 as a constant function, and the qx equal k squared in 1, and then fx, which is equal to 0. So you can see all three are continuous functions. They are all continuous, and we have a similar condition here. This is also px equal to 0, and then qx equal negative k squared, and then again fx equal to 0, and you can see that these all three functions are continuous functions because they are all constant functions. Constant functions are continuous functions, because if you draw the function, you get like a horizontal line, so which is a nice continuous function. So that means it satisfies the theorem, the condition of the theorem, and then you can see this is what you get. Okay, good. So let's have like a small note again. So another note. So you can see to find a unique solution, to find a unique means exactly one, unique solution. To find a unique solution, there should be two initial conditions. There should be two initial conditions. Why two initial conditions? Because there are two unknown. Since the differential equation is of second order, and we need two integration. We need two integrations. Each introduce one constant. Each introduces one constant. So that's it. So theoretically, if it is second order, you have two constant. If it is third order, you have three constant. So that means you need that many conditions to find the unique solutions. If it is a third order differential equation, you need there are three constant in the solution. So that means you need at least for the unique solution, you need three conditions to find them. Okay, now we have a very interesting another question. So let's see what's the next question. So the question is, suppose we find two solutions. Suppose we find two solutions, y1 and y2. Now the question is, can every solution be written as be written as y equal c1 y1 plus c2 y2? That's like interesting question. So if you know two solutions, so we are talking about second order differential equation. We focus on the second order differential equation. So if it is a second order differential equation, so if you know two solutions, can every solution be written in this form? If you know two solutions, can you write any solution like this? So let's look at a simple case. So for example, let's start with y double prime plus for y equals 0. So this one has two solutions. What are the solutions? y1 equal sine 2x, that's one solution, and y2 equal cosine 2x, that's the other solution. So if you know those two solutions, so yes, you can write the general solution using those two. You can write the general solution using those two. So in this case, it's a yes. Now let's look at another case. So let's see, these are all solutions. So let's say one is y1 equal sine 2x, that's one. The other solution is y2 equal 3 sine 2x. So these are two different solutions. But in this case, it's a no. You cannot use these two to write all the solutions. So that means there is something going on here. So y at one time yes and the other time no. So that means so those two solutions has to be what we call linearly independent. If those two solutions are linearly independent, yes, in that case you can write the general solution using those two. So the answer to this question is yes, if we can say y1 and y2 we're going to say different enough. That's not really mathematical, but it's easy to remember. Different enough. Different enough. So if they are different enough, then we can do that. So what's the different enough means? What we call linear independence. So let's talk about that. Linear independence. Linear independence. Linear independence. So this is a very important concept. So we can use some facts from linear algebra. So let's write it. So we say we know that if we have two vectors, so this is a fact from linear algebra. If we have two vectors, v1 v2, we call they are linearly independent if one is not a multiple of the other. So if v2 is not a constant multiple of the other one. So if this is the case, so if you cannot write one vector as a constant multiple of the other one, we say these are linearly independent. So that's the result that we learn from linear algebra. This only works for two vectors. It doesn't work for three vectors. Only for two vectors. Because in this case, so if you cannot write, that means you cannot put them like in one line. That's what it means. Either this way or that way. One go this way, one go that way. So that's the idea. So that means in this case, so we cannot do this. We cannot do this. So if you cannot do this, we call this a linearly independent. So that's not the case. So this is not the case. If this is not the case, then we say it is linearly independent. Okay, that's only for two vectors. It doesn't work for three vectors. So we say y1 and y2 are linearly independent. Are linearly independent if one is not a constant. If one is not a constant multiple of the other. Multiple of the other. So remember, these are not just vectors. These are functions, but we consider them in abstract sense. We consider them as vectors. So you can prove that because this is a function space. In that space, these functions become vectors. For example, sine 2x is a vector. Cosine 2x is a vector. Okay. So you can say consider y1 equals sine kx and y2 equal cosine kx as vectors, as abstract idea, as vectors. Good. So that's one way to say it. That's not really a good definition. This only works for two vectors. So when you have two vectors, if one is not a constant multiple of the other, so we say y1 and y2 are linearly independent if one is not a constant multiple of the other. So let's look at the real definition. So there's another mathematical definition. So what it says that, let's go for the general definition. So the actual definition of a linear independence. So the definition, a linear independence. Linear independence. This is the actual definition of that. So what it says that the functions y1, y2, like n functions are linearly independent, are linearly independent, are linearly independent if one cannot be written as a linear combination of others. Without being all coefficients 0. So in other words, so you can see there is, if let's say you have c1 y1 plus c2 y2, like that's, if let's say you're going to write it like that. This, in other words, if this is equal to 0, that means all the c1 c2 has to be 0. So that's the actual definition. If you write this as a linear combination, it should imply that all the coefficients has to be 0. So that is the actual definition of a linear independence. So if you try to write as a linear combination, it's not going to work. All the coefficients are going to be 0. If this is the case, we call this is linearly independent. Okay, good. So if not, the functions, are linearly dependent. So we call it a linear dependent. So that means if you can write one as a linear combination of this, we call it a linearly dependent. So that's why remember, like in the previous discussion, if you look at the previous one, so you say that, so v2 is not a constant multiple of the other. So that means if you can write, then it's linearly dependent. So the independent means no, you cannot write it. That means one is not a constant multiple of the other one. Okay, good. So it's a easy one. Okay, so let's go back. So we had that. Now what's going to happen in this case? So if this is linearly dependent, then we can remove one at a time all the linearly dependent ones. If you see something dependent, remove that. Then you look at the new set. If you see something linearly dependent, remove that. So once you keep removing, at the end you're gonna get a set which are all linearly independent. So we can say removing removing those dependent solutions, removing those dependent solutions from the set, we can form a linearly independent set. So that's exactly what we normally do. So if you see something linearly dependent, we're going to remove that dependent one at a time. At the end, there's a moment you're going to see that everything is nicely linearly independent. So let's do one example. So example, show that y1 equal sine x and y2 equal cosine x are linearly independent. So what we can do, to the contrary, we can assume that one is a multiple of the other. So suppose sine x equal a constant times cosine x. Now what's going to happen? So because we know that sine x and cosine, the x can be anything. So let's assume that they are linearly dependent. Sine x, one can write as a linear combination of the other. Now what we can do, then we can say, then for x equals 0, because x can be anything, if x equals 0, what do you get? You're going to get that sine 0. So you're going to get that 0 equal k times 1. So this means that k has to be 0. So that means if k is 0, so it says that k equals 0. So if you apply x equals 0, you're going to see that 0 equal k times 1. That means k equals 0. So if you get k equals 0, that means sine x equals 0. So you're going to get sine x equals 0 for any x, because k equals 0. Okay? K has to be 0 because k is a fixed number. Because k is a fixed number, that fixed number, you prove that has to be 0. Because here we assume that k is a fixed number. So you can write the one function as a multiple, fixed multiple of the other one. So k is a fixed number, but this has to be true for any x. But if you plug in x equals 0, you see that k equals 0. But when you put k equals 0, now if you go back to the original equation, it says that sine x equals 0 for any x. So which is not possible. It is not true. So that means you cannot say that they are linearly dependent, because if you say linearly dependent, this has to be true, but we prove that this cannot be the case. Okay. So thus sine x and cosine x is linearly independent. Okay, because if you suppose that one is a multiple of the other, we get this weird situation, what we normally call a contradiction, because it says that sine x has to be 0 every time, but that's not the case. So that means this is not true. So that means they are not linearly dependent. It has to be linearly independent. Okay, but and then now let's talk about this theorem. Actually, before that, we're going to talk about how to find the linear. So let's talk about like a nice result, and then after that I'm going to come back to this question how to find this in general. So let's talk about this nice result. It's another theorem. This is a very powerful theorem. So what it says that so let's say let P Q be continuous and y1 and y2 be two linearly independent that means one is not a multiple of the other, constant multiple of the other. One is not a constant multiple of the other. In two independent solutions to the homogeneous equation, to the homogeneous equation y double prime plus px y prime plus qx y equals 0. Then what it says that then every solution to the homogeneous equation can be written as y equals c1 y1 plus c2 y2. That means if you know any solution, it should be of this form. So this is a very powerful result, So if you know two solutions which are linearly independent, so if you know two solutions that are linearly independent, so we know two solutions which are linearly independent, then any solution has this particular form. Okay, any solution has this particular form. It is c1 y1 plus c2 y2. So this is called the general solution. This is called the general solution. It's called the general solution. Okay, so a general solution always has those two unknown like c1 c2 constants. So if it is a first order, you have one constant. If it is second order, you have two constants, which has two unknowns, c1 and c2, because this is second order. Good. So that's the idea. So let's do one example like that. So find the general solution of y double prime plus y equals 0. So this is something familiar to us, so we can write this. So the answer, we can write this one as y double prime equal minus y, that means k squared equal 1, that means k equal 1. It's a plus or minus 1, but we need only one of them. So that means we know the two solutions. So this says that one solution is sine kx. Kx means sine 1x in this case. That's one solution, sine 1x. and y2 equal cosine 1x. So that means what we're going to do, we're going to put two constants, right? So the general solution is y equal a constant times one function plus the constant times the other function. So that's the general solution. We still don't know actually where this sine and cosine coming from. That's we're gonna learn very soon, where these sine cosine coming from. But that's the idea. That's the result. That's coming from the theorem. So it says that if we know two solutions, then you can put two constant and write it like a cosine kx plus b sine kx, a cosine x plus b sine x, with two constants. So that's going to be the general solution of the differential equation. Good. Okay. Okay, so this one we can write as y double prime equal minus 1 squared y. So we can write like this. So that means k equal 1. You can see k equal 1. So then the two solutions are y1 equal cosine x and the y2 equal sine x. So we have those two solutions. So then we can write the general solution. So then the general solution, y is a constant times one solution plus a constant times the other solution. So this is where this is cosine x plus b sine x coming from, but we still don't know how to actually get this sine cosine. That we can learn very soon. Okay, so now let's try to understand a little bit more about the linear independence and how to prove the linear independence in a different way, so like general result. So let's talk about that now. So let's say how to check linear independence. How to check linear independence. So let's look at our differential equation y double prime plus px y prime plus qx y equals 0. That's a differential equation, along with y x naught equal b naught and y prime x naught equal b1. So we know that this is a second order differential equation. This has the general solution. So this has the general solution. This has the solution. Y equal c1 y1 plus c2 y2. So that's how you write the general solution with two constants. So the goal is to find c1 and c2. So let's see whether we can find c1 c2. So what we normally do, we're going to substitute the conditions. So let's say using the initial condition, we can write c1 y1 x naught plus c2 y2 x naught, this has to be equal to what? To the initial condition, that means b naught. Do the same thing with the derivative. So it is c1 y1 prime x naught plus c2 y2 prime x naught equal b1. Now what we're going to do, we're going to use some linear algebra. We're going to write this using what we call the matrix form. So if you write the matrix form, what we normally do is we can write the coefficient matrix, and then we can write the the multiplication matrix. So what we normally do is we can write the coefficient. So you can see c1 c2 c1 c2. So we can write this as like x variable. So we can write this one as y1 x naught, and then y2 x naught, y1 prime x naught, y2 prime x naught, and then just that, and then we write the c1 c2 like this, c1 c2. So we can write this in the matrix form. So this is what we call the matrix form. Matrix form. So we put the coefficients and c1 c2. So this is, so we had these are two matrices. First one is a 2 by 2 matrix. This is what we call a 2 by 2 matrix. There are 2 rows and 2 columns. This is 2 rows and 1 column. So 2 by 1 matrix. So and then on the other side you can write this one as b naught b1 like that. Good. So so that's the matrix form of this one. Now, so this is what we call a matrix equation. And according to linear algebra, so the goal is to, now what is the goal? So the goal is to solve for c1 c2. Now the goal is solve for c1 and c2. According to linear algebra, to solve this equation, we want to find the inverse of the matrix on the left side. To find the inverse, the determinant of that matrix should be non-zero. That determinant is what we call the Wronskian. So, so let's write that. So let's write the idea. So we call the Wronskian. So so we can solve the system. We can solve the system if the determinant y1, when you write the determinant, you write 2 vertical bars. For matrices, we use either square bracket or the parenthesis notation, but for determinant, we use vertical bars. y1 x naught, y2 x naught, y1 prime x naught, y2 prime x naught not equal to 0. That's what we call invertible. If the determinant, this is what we call the determinant. This is called the determinant. This is a notation. Okay, that's not absolutely here. It's a determinant. Okay, if the determinant not equal to 0, this determinant is called the Wronskian. This is called the Wronskian of the differential equation. The notation is this, so we write w y1 comma y2, this is how we write it. That's the determinant of, first we write the function y1 x naught, y2 x naught, y1 prime x naught, y2 prime x naught. This is what we call the determinant at x naught. That's the determinant x naught. So this is what we call the Wronskian. This is a Wronskian. So we use a Wronskian because it's easy to find whether the two functions are linearly independent. So we can do a problem from that. So let's try a knot. So if the Wronskian is not equal to 0, is not equal to 0 at some point x naught. Okay, it doesn't matter what the point is, just some point. At some point x naught, we say the solutions y1 and y2 are linearly independent. So now how to find the determinant? So let's write that determinant of 2 by 2. Determinant of 2 by 2 matrix. So determinant of 2 by 2 matrix, this is an easy one. So if we have a 2 by 2 matrix, let's say we have A, B, C, D. The determinant of 2 by 2 is you multiply the diagonal entries first, so that means you multiply AD, and subtract, you multiply BC. So that's the determinant of a 2 by 2 matrix. So if we have like 4 numbers like that, we first multiply the first diagonal. So we multiply this diagonal first and subtract that diagonal. Okay, so plus and minus. So it's AD minus BC. That's the determinant of a 2 by 2 matrix. Now let's try to use this idea to like a regular problem. So let's do this one. For example, we found that y1 equal e to the negative 2t and y2 equal e to the negative 3t are two solutions of R, y double prime plus 5y prime plus 6y equals 0. Find the Wronskian of y1 and y2, and then check whether y1 and y2 are linearly independent. Then, because we know that if they are linearly independent, then you can write the general solution. Write the general solution of the differential equation. So that's a problem. So the answer So the Wronskian W y1 y2, which is the determinant of y1 y2 y1 prime y2 prime. So let's plug in. This is e to the negative 2t, e to the negative 3t, and take the derivatives. So it is negative 2 e to the negative 2t, negative 3 e to the negative 3t. Now we can use the multiplication. We multiply the first diagonals. You multiply the first diagonals, you're going to get negative 3 e to the negative 2t e to the negative 3t, and the minus with this minus become plus 2 times e to the negative 2t e to the negative 3t. If you simplify, you have negative 3, negative 2, so negative, you get e to the negative 5t, and you know that this never equal to 0, so that means